For the past few months, I've been working on creating a free platform for aspiring actuaries to study for their exams. I figured a good place to start was with a quiz system to supplement the recommended textbook reading. Since the Society of Actuaries offers a version of this for the first two exams, probability and financial mathematics, the next most popular exam, statistics for risk modeling, commonly referred to as SRM, seemed like a good candidate. For SRM, the Society of Actuaries has a published bank of about 70 sample questions available to practice with. As anyone who has taken an actuary exam knows, it's not unusual to do 1,000 or more practice questions to prepare for an exam, so 70 doesn't quite cut it. Considering this, I felt a good starting place was to take the existing 70 practice questions and write some code to automatically generate variants of the questions, the way you might see on a platform like WebAssign or Newton. I figured this would be an easy task that wouldn't require too much thought, but while working through the code for some of the questions, I came across a couple of problems that were a lot more complicated than I expected. This video was created to showcase these problems and how I went about solving them. Of course, I'm no professional programmer, and my solution isn't the only solution, so if you have a better way to go about solving these problems, let me know. I'm curious to see what other people come up with. And if you're interested in problems like these, or you want to keep up to date with progress on the website, remember to subscribe to the channel. Without further ado, let's get to the math. First problem I wanted to showcase is question 15 from the SOA sample questions. This problem asks us to perform one iteration of a k-means clustering algorithm on a set of data and find the size of the cluster with the fewest data points. For those of you who don't know about the k-means clustering algorithm, or just need a little refresher, let's walk through how the algorithm works. The purpose of the k-means clustering algorithm is to identify structure in a dataset, grouping data points into k-many clusters where k is chosen in advance. More specifically, the algorithm is defined as follows. Given a collection of data points, first, randomly assign cluster labels to each data point. Second, calculate the centroid of each cluster. Third, reassign cluster labels for each point based on the closest cluster centroid. And then 4, repeat from step 2 until the labels don't change between iterations. In our specific problem, we were given 12 data points with their initial cluster assignments and asked to perform a single iteration of the algorithm. Calculating the centroid of each cluster, we received the following values. Now, we just need to iterate through each point, finding the closest cluster to it and updating the label for our point to be the closest cluster. After doing this for every point, we see that cluster C is the smallest cluster with 3 points, giving us our answer. Now that we know how to solve the problem, our goal is to change the inputs to the question, in this case, the 12 given data points, such that the question is as close to the original as possible. This means 1, there are no duplicate values, 2, no points fall exactly on a cluster center, and 3, all cluster centers fall on a grid point. The immediate impulse is to just naively select the data point at random, ensuring that each condition is met. While simple, a quick simulation of 1 million possible cluster combinations only found 15 valid entries. While this can certainly be improved with some careful conditioning, we'd rather avoid the issue altogether by coming up with some method of guaranteeing valid clusters in a fixed number of steps. To fix this issue, we will actually start by picking our cluster centers first, before any particular points are chosen. Since the cluster centers in the sample problem are all pretty close to the origin, we'll limit the centers to be close to the origin as well. Now, for each centroid, we want to pick 4 points such that our previous conditions are met and their centroid doesn't change. To accomplish this, we will start by picking the 4 points to be the corners of the square surrounding the center. Assuming these points are valid, we could stop here, but we want to allow more randomness in our inputs. So we're going to move the points randomly according to the following rules. Rule 1, points always move 1 step in a given direction. Rule 2, points can never move closer to the center, only further. So this means the top right point can only move up and to the right, and the bottom right point can only move down and to the right. This ensures that there are no duplicates, since the points can never cross the lines running through the x and y coordinates of the centroid. And rule 3, every time a point moves, a random point will be chosen to move 1 step in the opposite direction to ensure the centers remain constant. We will randomly select points to move according to these rules for some fixed number of steps, and at the end, if any of our points are invalid, we will move the point however many times required until the point becomes valid again. Now our clusters seem to be initializing properly, but when we try to run the k-means clustering algorithm, we sometimes end up with an error. We can see that the error happens when there is a data point that falls perfectly between 2 clusters, and our clustering algorithm doesn't know what to do. We avoid this by simply checking to make sure that each data point can be properly assigned to a unique cluster, and if not, move that point 1 more step. Now our clusters generate correctly, and we can find our correct answer. Cluster B is the smallest cluster with 3 data points. I found this problem interesting because while, theoretically, using random inputs is quick, when human patience is a consideration, it's often better to pick an algorithm with a consistent runtime, even if it's slightly slower on average. if our first problem was interesting as a puzzle-solving exercise, our second problem is interesting in a way only pure math can be. Our second problem comes from question number 4 from the SOA's practice problems. In this problem, we are given a random walk and asked to find the standard error of the 9-step ahead forecast. A random walk, commonly referred to as a drunkard's walk, is a stochastic process that traces out a series of random steps, like a drunkard stumbling around randomly. More precisely, we can write a random walk as y sub t is equal to y sub t minus 1 plus c sub t. So our position at any time t is equal to the previous position plus some random step size c sub t, where we will assume that c sub t follows a normal distribution. When the mean of c sub t is non-zero, we say that y sub t is a random walk with drift. So we can't say in advance exactly what y sub t plus 1 will be, but we have an idea of the general direction it will go, like a drunkard who we know is trying to walk home but stumbles occasionally along the way. In our specific problem, we are given 10 steps of a one-dimensional random walk, starting at y equals 0 and ending at y equals 30, and asked to find the expected error of the 9-step ahead forecast. The standard error of an h-step forecast is just the standard error of a random variable times the square root of h. To calculate sigma, we first calculate our observed values of c sub t, then use the normal population standard deviation formula. From here, we simply multiply sigma by the square root of our forecast length, giving us our final answer of 4. Once again, we want to find some way to programmatically change the inputs to this problem while keeping the new problem as close to the original as possible. Thankfully, the question writers were clever when creating this problem and chose the number of observed points in the forecast horizon such that their impact on the final answer cancels each other out. Due to this, the final answer only ends up depending on the values of c sub t. So, if we want our final answer to be some number n, we need to pick our c sub t such that 1. The sum of their squared distance from the drift is n squared, and 2. The average of the c sub t is equal to our chosen drift d. Replacing c sub t minus d with the variable delta, we can rewrite this in simpler terms. Using this simplified expression, our new goal is to find some sequence of numbers delta sub t such that 1. The sum of delta sub t squared is n squared, and 2. The delta sub t is summed to 0. While we could randomly guess at values of delta sub t until we find a valid combination, it's relatively easy to brute force this problem. Given a target value n, we can use recursive backtracking to systematically explore all combinations of delta sub t values, finding all combinations that satisfy our variance and zero-sum conditions. Doing this for a few small values of n, we can see an interesting pattern appear. When n is odd, it seems that there are no combinations of delta sub t that satisfy both conditions. A sample size of 4 is promising, but does not constitute a proof. So let's see if we can prove it. To prove this, we first need the fact that if n is odd, then so is n squared. Now, our first condition states that the sum of delta sub t squared is equal to n squared. Since we assume n is odd, so is n squared. Now, we will split our sum into 2 parts, the sum of the even terms and the odd terms. Since the sum of the even delta sub t squared is even, the sum of the odd delta sub t squared must be odd. Since delta sub t is odd, so is delta sub t squared. Now, the sum of odd numbers is only odd if we are adding an odd number of terms, so we must have an odd number of odd values of delta t. To satisfy our second condition, we need the sum of the delta t's to be 0. Once again, splitting the sum into the even and odd terms, we can see that the sum of the odd terms needs to be even. Like the odd case, this is only possible if we have an even number of odd terms, a contradiction since to satisfy condition 1, we needed an odd number of odd terms. Thus, it's impossible for our final answer to be odd. On the flip side, when n is even, by definition, we can write n as 2 times some integer k. So n squared equals 4k squared, meaning the following sequence of deltas is valid. Thus, anytime n is even, we could find at least one set of valid inputs. As for the actual implementation, I took the easy way out this time. For n equals 4, most of the 156,240 valid combinations of delta t use the same numbers just shuffled around. So if we ignore the order, there are really only 10 unique combinations. This means it's easy to just store these 10 combinations, then when generating the question, we can randomly select one and shuffle it, giving us access to all 156,000 combinations while only storing 10. As a math major, this problem is definitely my favorite of the two. It took me a long time to realize that the lack of odd solutions was something structural about the problem and not just a bug in my code. Once I came to that realization, the problem suddenly got a lot more interesting. Thanks for joining me on this dive into 2 fascinating challenges hidden in seemingly simple problems. I hope you found a little insight or at least some good puzzle fodder to take away. Remember, math isn't just equations on a page, it's a tool we use to solve real problems, even in unexpected ways. If you enjoyed this exploration, please hit the like button, subscribe for more deep dives and practical challenges, and leave a comment below with your thoughts on your own approaches to these problems. Until next time.